Hello everyone, in this video we are going to discuss the experiment of measurement of capacitance by SAUTY modified bridge. First of all, we must know what is this SAUTY's modified bridge. Earlier I had uploaded a video on Phasor bridge. Also we know meter bridge. They both work on the principle of Wheatstone bridge. So SAUTY bridge also works on the same principle, but this is used to measure the capacitance as it is written over here. And earlier what we did was Phasor, that was needed for measurement of resistance. So the difference here is that this is used to measure the capacitance. So first of all, I'd like to give you a brief idea about what we are going to discuss in this video. We are going to first of all discuss the theory, objective, circuit diagram, and this as a whole. I'll explain these things. Then we are going to see the procedure what you have to write in your files, and also we will do the simulation. If you have not performed this in your lab, then we can do it here. Here is the online simulation where we can change the values like this and from here. So I'm just giving a brief idea what we are going to discuss in this. Also there is a quiz. We will solve some questions. These are some MCQs which might be asked, so we will discuss them also. And at the last I'll provide you with the file where you can see the readings and copy down in your own file. So let us start with the theory. First of all, objective. In this bridge, a capacitance is measured with standard variable capacitance. The connection is shown in the figure. The bridge modification of SAUTY bridge. This bridge is the modification. What is difference here? That capacitance with resistance is present here. This is, we are giving name as C1 R1, here C1 R2, and these are the resistance. So in Wheatstone bridge, what we had seen earlier was that here is the resistance, here is resistance, here and here also. Main concept was the ratio of the resistance. Here, in this wire, no current passes through it. It means the null detection. Also sometimes this is asked in Viva, that as a whole, in a single word, how can you describe the principle? So that is null detection method. It is also known as, where the current does not pass through this wire. This means that the potential about this point and this point is same. So this also works on the same principle. Difference here is that there are two capacitance present. Also we have to find one unknown capacitance, and here we will let it to be C2, that we are going to find C2. So here current flows, and this is shown I1 current goes here, I2 goes here, same I1 here and same I2 here. We know that this sum remains the same. So I1 plus I2, and here also I1 plus I2. जितना आ रहा है उतना ही जा रहा है. We had studied this in Kirchhoff's law also. So here C1 a standard capacitor, C2 a capacitor whose capacitance is to be measured. We are going to measure this capacitance. R1 and R2 representing losses of their corresponding capacitors. This R1 and R2, these will represent the loss in the capacitor, and these are the actual resistance. They are shown by capital R1 and R2. So this is the difference. So R4 and R3, these are known inductive resistance, and R1 and R2, they are connected in series with C1 and C2. So these are connected in series. R1 is in series with C1 and R2 is in series with C2, and these are known inductive resistances. So at the balanced condition, what happens is, we know very well that the ratio equals. So how we will describe it, that the principle is of Wheatstone bridge null detection method. When bridge balances, the ratio of impedances are equal, this balance can be obtained by varying these resistances. These one, capital R1, R2, R3, R4, we can vary these to get the ratio of impedances to be equal. So what here shown is, this is your Z1 actually, this is Z4, this is Z2 and this is Z3. What it is, what you can see from here, that this whole resistance, so this includes R1's resistance, capacitance resistance. So this is written as capital R1, this is your small r1, this is the representing loss of their corresponding capacitors, small r1 and r2, and 1 upon j omega c1, this is the resistance of the along this capacitor. Similarly, we can write it for here. Balancing here means that resistance of this, if we had named it as A, B arm, resistance of this arm divided by resistance of this arm would have been equal to R3 upon R2. So they have multiplied directly, so this is like this. Simply by solving this, you can see very simply they have multiplied by taking these two in bracket, R4 is here, and then equating both real and imaginary parts and then separate them. Real part R4 upon R3 is equals to R2 plus small r2 upon R1 plus small r1. So this is simply by solving these equations. Equation is by same principle of Wheatstone bridge, that was the ratio of impedances is equal. And I like to clear if you have any doubt here, that we are equating real part, so this part is the real one, right? And where this j, or you can say it as, obviously you would have taken it I also, this is iota, the imaginary part, they have represented it by j. We could have opted like I, so this is our own choice. So equating then the imaginary parts, and then we are going to separate them and solve, and this is what the equation we are going to find out. Then again putting these values, we can find C2 is equals to this, and we can also write it like this simply by putting this equation here. This is the value we get, and simply what you can keep in your mind is this last equation, equation 1, which is mentioned as C2 upon C1, that is the ratio of the capacitance, that is equals to R1 plus small r1, R2 plus small r2, and this is equals to R3 upon R4. And again you can see from here that R1 and R2 small 1 were representing the loss of their corresponding capacitors, and these capital R4 and R3 were the known inductive resistance, and these R1 and R2, they are connected in series with C1 and C2 respectively. We can see from here, simply you can just keep this in your mind and then remember these equations, and there is nothing very hard here. It's just like they have balanced the circuit, and this is the equation we got. Next we have the phasor diagram. You can just see it many times. This is not asked in exams, but still you can just have a look. We know that in case of inductor and capacitor, there is difference in phases in voltage and current. Now I would like to share my own personal method of learning that where in which case the inductor or in capacitor, where the voltage or where the current lies ahead or behind. So how I remember this is like a term ICE, I-C-E, I-C-E. C is capacitor. If I is before C, It means current is before voltage in capacitor. So you can just have your own method of remembering this. If you can just remember it by yourself, there is no need to get confused. This was my personal method. It's like you will never forget this thing. Obviously, in capacitor, I, which is the current that leads voltage, and in inductor, opposite follows. Just following this rule, you can draw this phasor diagram if required. Now main thing here is the phase angles. Phi 1 and phi 2. These are the phase angles of C1 and C2 respectively. The capacitance, their phase angle, they are given here. Dissipation factor. This is very important thing in this experiment. Dissipation factor. What does this actually? You can simply explain it to be the tangent of loss angles. We can say these as loss angles, and we can say dissipation factor is the tangent of loss angles. This is tan of phi 1 and tan of phi 2. But what is the significance of dissipation factor? What can be explained if asked to define? So you can say that this is the reciprocal of qualitative factor. Reciprocal of qualitative factor. What is qualitative factor? It defines the quality. Simply it defines the goodness, the quality. So it is the reciprocal of that. It in case significance is asked. Otherwise simply you can say that dissipation factor is the tangent of phase angles phi 1, phi 2. So right, now we can just proceed further, I think. So here we are taking D1 and D2, two dissipation factors. D1 is equal to tangent of phi 1. Also what it can be written like frequency into capacitance into the respective loss of that capacitance, that is small r1. Right, similarly in case of D2, again you know this equation, we had found this earlier here, right? Just from here we are using it like this. Then we are going to multiply omega both the sides like this. Then we can find the difference, and this is the equation which you can keep in your mind. So therefore, if the dissipation factor of one of the capacitor is known, dissipation factor of other can be determined from this formula. Is it easy? Yes. Next, proceeding to the procedure, I'll provide you the link of this online lab in the description box also. So we know this circuit. Procedure is set the voltage V is equals to 3 volt, frequency 50 Hz. Very important question. This is AC frequency, and this bridge is also AC bridge. Also you must know that the frequency which is coming to our house, to our home, to our shops, here in India it is 50 Hz AC frequency, and obviously we know that transformers are present which convert it into DC. Otherwise this question can also be asked that what frequency is coming to our house. This is like very normal question, it can be asked. So in this circuit also we are taking voltage is equals to 3 volt, frequency is equals to 50 Hz. Also set the unknown capacitance value from set capacitor value tab. Switch on the supply to get millivolt deflection. Very important, we are getting the deflection in millivolt. You must know that millivolt is equals to 10 to the power what? X can be asked. So it is 10 to the power minus 3, 0.001. You can also say it like watt per ampere. Watt, W-A-T-T, watt per ampere. Ampere is of current. Obviously this can also be asked. So next, choose the values R1, R2, R3, R4 and C1. This is what we are going to choose, and C2 is what we are going to find out. I'll show you this as a whole in the simulation we are going to perform further. Observe the millivoltmeter pointer to achieve null. We know what actually this is. Null deflection principle is used here. If null is achieved, switch to measure capacitance value tab and click on simulate. Observe calculated values of unknown capacitance C2 and unknown internal resistance R2 of the capacitor. Obviously, if C2 is unknown, then R2 will also be unknown. So, also observe the dissipation factor of the unknown capacitor, which is defined as you can see from here, and now I am going to start with the simulation. So I'll provide you the link in the description box. Procedure is again given here. It is very same as what I have done earlier. So I'll start with this. Whole of the screen cannot be shown at the same moment, so I'll provide the link. You can open it by itself. I'll try to show you. Here we can change the values, like from clicking here. First of all, here this is given, set the capacitor value. This is what we need to do first of all. So I can set it as per my wish. So let it be 0.454. Set, click on set. Okay. Then here you can change the values as per your wish. Let it be same if you want it to be same. I want it to be same, so let it be same. You have to click here. You can see the deflection. Earlier it was here and it is deflected this much. You can also note down this reading. So I am not going to do here for each and every. I'll give you the readings at the end. So I'm just showing you here that you have to now switch off this. This is the button, switch on, switch off. NA, this means nothing. You have to perform again and get some reading. Here some controls are also provided. You can change the value of R1, R4, R3, R2, C1, obviously, because we are going to find for C2. We will find it from the formula. We can change the value of R1, R2, R3, R4 and C1, but unknown is C2, which we are going to find from this deflection. This is your null deflection. You can change the value and this will get deflected. I am facing some problem here because I can't show the screen whole. So I'll just provide you with the readings and this link. You can perform it by yourself. Here I am changing. Okay. Let it be 0.0472. Set. Click on set. So you can change these values also and then you'll get some reading over here. I'm just going to show you the readings table. So this is what we have discussed earlier. This is how you will write in your practical file. Aim to measure the capacitance with a standard variable capacitance using modified SAUTY bridge. Connections are shown in the figure. You will have to draw this and you have to write what these represents. Then in theory you can write it like obviously principle. Then what is the advantage? Important. Can be asked in your viva also. Advantage of this bridge is its simplicity, because some bridges which also measure capacitance but they are very very complicated. This bridge is simpler as compared to them. It is impossible to obtain the balance if both the capacitors are not free from dielectric losses. Thus, with this method, only lossless capacitors like air capacitors can be obtained. So again, this is shown the balanced condition which we have discussed. You can take the screenshot if you wish. This is the second page and here is the calculations and your readings. Finally, what is required. So in this table you can see the actual value C2. This is the list of the readings. Resistance in ohms, this, C1, this, C2, this, and R2. Always we are finding it to be 5. And this is the dissipation factor. You can note down and it will be better if you perform by itself. So I'll provide you the link in the description box. I am zooming it in so that you can note down clearly. This is the calculation. Percentage error can be found. This is the formula. Tested value minus standard value. Standard value is the value of unknown capacitor which we set. Tested value is the value which we get from the experiment. So percentage error is the subtraction of both. When tested value is subtracted from the standard value, means the value which we get from experiment, that is subtracted from the value of unknown capacitor which we set. So from this formula you can find the percentage error. These are the readings, so you can just note it down. You can take the screenshot if you require it. Also, I'll provide you the link. So thank you for watching the video. Hope this was helpful. I'm showing the screen once again. This is how you have to write in your file. Page number 2, page number 3. Fine. If you like this value, found it to be valuable, so do click that like button. That will motivate me to put more videos like this. Thanks for watching.